As I mentioned before, there are many fundamental particles, but the world that we live in is really made up of four main fundamental particles. One of them is no surprise to you, it's not new: electron. The other one is a electron neutrino. The electron has a very small mass compared to the nucleus of the atom. And this neutrino character is possibly has no mass at all, but at least it has a million times less mass than the electron. So it's very, but it does account for the mass that we are living with. Then there are two quarks, an up and a down quark. Notice I did not mention a proton, I did not mention a neutron. The quarks are involved in coming up with the protons and neutrons. Now, what's a practical application where we can see some of these fundamental particles? Carbon 14 is a radioactive element. It decays into stable nitrogen 14. So that beta decay is going to produce an electron, and it's going to produce an antimatter neutrino. The electron neutrino that I mentioned also has a counterpart, which is a long-lived particle, the antineutrino. Now, the electron has its counterpart too, the positron, but the positron is quickly annihilated as soon as it meets up with an electron. Positron is positive charge, electron negative charge. So they attract one another and they annihilate each other. Let's have a quick review of carbon and nitrogen. Carbon, 6 protons. Nitrogen, 7 protons. And of course, to keep the charge balanced, a carbon atom has 6 electrons, a nitrogen atom has 7 electrons. So, what is the number of neutrons? Well, the number of neutrons can vary. The charge can still be balanced. The chemical properties can still be the same because the chemical properties are pretty much the electrons that are on that shell and how they combine with other atoms and combine with themselves. But what about the neutrons, and why would you have different numbers of neutrons? Well, I'm going to start up in the sky. I'm going to start up in the sky with nitrogen. Nitrogen, 7 and 7. Ah, nice and balanced. 7 neutrons, 7 protons, and then all of a sudden I have cosmic neutrons. Neutrons that are super strong and high energy, and they hit the nitrogen, and they knock out a proton and leave a neutron. So I've got 8 neutrons now and 6 protons. If I got 6 protons, then what happens to that extra electron out there? Well, that extra electron isn't attracted, it just goes away. So now I've got carbon 14 up in space. And I can create carbon dioxide out of carbon 14. But what happens to carbon now? It's got 8 neutrons and 6 protons, and that's unstable. So, how does it stabilize? How does it stabilize itself? Well, here's what happens is that the neutron can actually have a little bit higher mass, so it's a little bit more unstable. So the neutron can actually get rid of and uh, what am I missing? I'm missing something. The neutron can actually get rid of an electron and an electron. Remember that electrons have a lot to do with the chemical properties. It can get rid of an electron, and in this process, it actually emits this other thing called an antineutrino. Antineutrino. Now we've got something other than protons and neutrons that we're talking about. And just think of it. That means that protons and neutrons must not be the elementary particles. There must be some junk inside those that'll allow these other things to happen externally. Otherwise, how could a neutron turn into a proton and vice versa? It just doesn't really, there must be something going on. And that's internal inside these things, and that's the quarks. And somehow I'm going to get to the quantum mechanical justification or the theory behind these quarks. Did somebody just make them up and give it a silly name like a quark? And, we're all fooled by their ideas. So I hope that gives you kind of an idea of what's going on with the carbon and nitrogen cycle. And while I'm here talking about carbon 14, it's going to decay. And remember, the carbon 14 has a whole bunch of these atoms that are in this carbon dioxide stuff. Now, how do we get carbon dioxide down here? Well, the plants sucked in and breathed in the carbon dioxide, and the plants made some food where the animals ate that food, and the carbon 14 is still in their bodies because we eat that food and it has that carbon dioxide, which then becomes a carbon based food material. Then we eat that stuff, and there's a certain amount of carbon 14 at the time you eat it, certain standard percentage on Earth, and then that slowly decays. So the amount of carbon 14 slowly decays after you're dead, and that allows you to do this carbon 14 dating. And the carbon 14 dating says that half of that carbon is going to disappear in somewhere around 5,700 years, 5,700 years. And those half-life amounts can allow us to predict how old something is if we have the carbon stuff in there. Now, my next step, if it ends up getting into this video or not, is to talk about this thing called beta decay, which is when the carbon changes. The carbon emits an electron and one of these anti-neutrino things. Going to look at Fermi, Enrico Fermi, who proposed this idea. He was a theoretical physicist at the time and changed to be an experimental physicist after he started proposing some of these subatomic particle ideas. He proposed a theory which is still good today.